Hello everyone and welcome back to chemistry class. Let me start with a thought. Have you noticed how arranging books by size instead of subject makes it difficult to find the one you want? Something similar happened in the history of chemistry. Mendeleeff arranged elements in his periodic table based on their atomic masses, and although it was revolutionary at the time, it led to some serious problems. For example, iodine had a lower atomic mass than tellurium, yet its properties matched halogens like chlorine and bromine, not with tellurium's group. This forced him to place iodine after tellurium, which looked incorrect if atomic mass was the deciding factor. Then came isotopes, atoms of the same element with different atomic masses, which completely confused the classification because chlorine 35 and chlorine 37 could not fit logically. Even hydrogen had no fixed place, behaving sometimes like an alkali metal and sometimes like a halogen. So, just like a messy bookshelf, Mendeleev's arrangement created anomalies, and chemists were searching for a more reliable basis of classification. Now, here's where the story gets exciting. In 1913, Henry Moseley performed experiments with X-ray spectra of elements and discovered something groundbreaking. He proved that the true fundamental property of an element is not its atomic mass but its atomic number. That's the number of protons in the nucleus, or equivalently, the number of electrons in a neutral atom. With this shift, all the confusion vanished. Suddenly, iodine and tellurium fell into their correct groups because iodine has atomic number 53 and tellurium has 52. Arranging by atomic number made everything fall into place beautifully. This idea became the cornerstone of the modern periodic table. Remember this key point: it's not the weight of the atom that determines its position, but the charge of its nucleus, the atomic number. Moseley's work gave the periodic table a rock-solid scientific foundation. So, what is the modern periodic law? Here it is, stated clearly: the physical and chemical properties of elements are periodic functions of their atomic numbers. In simpler words, when elements are arranged by increasing atomic number, similar properties repeat at regular intervals. Take lithium with atomic number 3, sodium with atomic number 11, and potassium with atomic number 19, though their masses are quite different, all behave as alkali metals with one valence electron. This repetition of similar traits is called periodicity in properties. Why does this happen? Because the electronic configuration of the outermost shell repeats in a predictable manner. Every new period begins when a new electron shell starts to fill, and that's why the same type of chemical behavior appears again and again. The modern periodic law gave us a periodic table that not only corrected the mistakes of the past but also predicted the chemistry of elements with surprising accuracy. Now, let's dive deeper. Why exactly does periodicity occur? The answer lies in the recurrence of similar valence shell electronic configurations at regular intervals. Think of group 1 elements, hydrogen excluded, lithium, sodium, potassium, rubidium. Each has one electron in the outermost s orbital, written as ns1. That's why they all share common properties. They are soft, highly reactive metals, and they readily lose one electron to form positive 1 cations. Across groups, properties remain similar because the valence shell configuration is alike, while across a period, properties change gradually because electrons are being added one by one to the same shell. This leads to observable trends known as periodic properties: the atomic radius, which is the distance from the nucleus to the outermost electron; ionization potential, the energy needed to pull an electron out; and electron affinity, the energy released when an atom gains an electron. These properties rise and fall in patterns that repeat as we move across the table, and that is the beauty of periodicity. Now, let us look at how the modern periodic table is arranged. You'll see 7 horizontal rows called periods and 18 vertical columns called groups. Each period corresponds to filling a new electron shell, starting with hydrogen and lithium and moving right across to noble gases like helium and neon. The vertical groups bring together families of elements that share common traits because their outermost electronic structures are the same. Groups 1 and 2 make up the S block, groups 13 to 18 form the P block, and the central chunk, groups 3 to 12, are the transition elements or D block. Below the table, we often place 2 extra rows, the lanthanides and actinides. These are the F block elements. This systematic arrangement allows chemists to locate an element instantly and even predict its behavior. On your screen, you can see the complete modern periodic table. Notice how the elements are beautifully organized like a map of chemistry itself. Let's zoom in further on periods and groups. Each period begins with an element having just one electron in a new shell and ends with a noble gas having a completely filled shell. For example, the second period starts with lithium, electron configuration 2,1 and ends with neon 2,8. Across a period, metallic character decreases and non-metallic character increases. It's a smooth transition from reactive metals on the left to noble gases on the right. Now think about groups. All elements in a group have similar valence shell configurations, so they behave in very similar ways. Group 17, the halogens, fluorine, chlorine, bromine, and iodine, each has 7 valence electrons and tends to gain 1 electron to form -1 ions. On the other hand, Group 18, the noble gases, are chemically inert because they already have filled outer shells. That's why helium balloons don't react with the air and stay safe to use, a practical application of periodic table knowledge. Now let's solve an example to see how powerful the modern periodic table is. Suppose we have an element X with atomic number 17. First, let's write its electronic configuration 2, 8, 7. That means it has 7 valence electrons. Immediately, we can place it in group 17, the halogens, and in period 3. Now, what can we say about its properties? It will form a -1 ion by gaining an electron. It will be highly electronegative, ready to pull electrons from metals. It will form salts such as sodium chloride, where sodium gives 1 electron and chlorine takes it. Yes, element X is chlorine itself. This shows the predictive power of the periodic table. Even if you encounter a newly discovered element, its atomic number will tell you its exact location and most of its properties. That's why scientists could predict aluminium, which later turned out to be gallium, and even noble gases before they were isolated. So, let's wrap up today's discussion. We started by seeing the defects in Mendeleeff's periodic table, such as the wrong placement of iodine and isotopes. Then we explored how Henry Moseley's discovery of atomic number as the true basis of classification solved all anomalies and led to the modern periodic law. The physical and chemical properties of elements are periodic functions of their atomic numbers. We saw that periodicity arises from the recurrence of similar valence shell electronic configurations, giving rise to trends in atomic radius, ionization potential, and electron affinity. Finally, we examined the structure of the modern periodic table with its 7 periods and 18 groups and solved an example predicting properties based purely on atomic number. I hope you now see how the periodic table is more than just a chart on your wall. It is the very roadmap of chemistry, guiding us to understand, predict, and even discover new elements. With this strong foundation, we are ready to dive into periodic trends in the next session. Until then, keep the curiosity alive and remember, chemistry is everywhere, shaping the world around you.